Okay, these are the basic trig identities that we're going to look at in Lesson 6a here, and this unit is all about analytical trig, which gives us the opportunity to dive in really deep and understand how these functions work and behave. And we're going to explore some applications with these functions throughout the course of this particular unit, but at the same time we also need to focus in on knowing the identities downright cold. And the identities that I'm referring to are these reciprocal identities, which are things that we already know, cosecant being 1 over the sine, secant being 1 over the cosine, cotangent being 1 over the tangent. And those reciprocal ones work as well, so sine is 1 over the cosecant and so forth. And then we've got these quotient identities right here, which we've already alluded to. Tangent is sine over cosine, and cotangent is cosine over sine. Well, that makes a lot of sense, because if you think about the cotangent being the reciprocal of the tangent function, then that sort of holds here with the quotient identities. So these ones on the left, the ones that I've highlighted, you definitely need to know those and have those memorized and down cold. I know we've already kind of done some work with these in the previous unit, but we're going to be applying these a little bit more in this one for sure. Then we come to these even and odd identities, and that has to do with the fact that the sine, cosecant, tangent, and cotangent, those are all odd functions, and the cosecant and secant are even functions. So what does that mean to be an even function? Well, that means if I take the cosine of the opposite of the number, it's the same as taking the cosine of the number itself, and same with the secant. So if you take the sine of the opposite of a number, you're going to get the opposite of the sine. So it's an odd function for sine and cosecant, and also for tangent and cotangent. All right, then over here we've got these cofunction identities, which those don't come into play very much. I don't see much of those in calculus in the times I've taught that class before, but in terms of our class here, these may pop up sort of when you least expect it. So the secant and the cosecant differ by a phase shift of pi over 2. And you could say the same thing about the tangent and cotangent and the sine and the cosine. I've kind of alluded to that when we talked about the graphs, that the sine and cosine differ by that phase shift of pi over 2. So this is just something that kind of cleans up that idea a little bit more. Really what this means in terms of a trig function is, this is like saying the sine of 30 degrees is equal to the cosine of 60 degrees. So the two are complementary angles, they add to 90. So the sine of one angle is equal to the cosine of its complement, and you could make that case for the tangent-cotangent relationship, secant-cosecant as well. Okay, well, it shouldn't, and this one shouldn't surprise you, because the sine of 30 is 1/2 and the cosine of 60 is also 1/2. Hopefully you knew that from your unit circle. Alright, so how are we going to apply these in this particular lesson, now that I've kind of introduced them? How we're going to apply them is we're going to use them to simplify trig expressions down to a simple trig function here. So in this first example, where we have the cotangent, secant, and sine all being multiplied together, if we want to condense this down to a single trig expression, we certainly can. It might be helpful to change everything in terms of sines and cosines, and that might help reveal the result when we're all said and done. So the cotangent can be rewritten as cosine of some angle theta over the sine of that angle theta, and then the secant, okay, let's see if we can get a dot there. Let's undo that, and there we go. The secant is 1 over the cosine. Let me fix that real quick. And then we have just a sine function out to the right here. So if you notice, the cosines will cancel, the sines will cancel, and what we're left with is just 1. So that's what's meant by condensing it down to a single trig expression. Even though we don't have a trig function in our final answer, we had all those trig expressions that sort of canceled out, and washed out to 1 when we canceled out common factors. Okay, so let's go ahead and talk about this one in the middle here, this cosine times the secant, and then you've got a cotangent as well. Well, if you were to have the cosine and secant, you know that those are reciprocals of each other. So cosine and secant multiplied together will multiply to 1, and then you have the cotangent of some angle alpha. Okay, well 1 over the cotangent, that's the same thing as saying the tangent of some angle alpha, and that's what we're looking for in that situation. Just condense it down to one expression. Alright, let's take a look at example 3 here. And as we do, we know that the tangent and the cosecant are both odd functions from above. So this is like saying negative tangent of x times negative cosecant of x. Well, the negatives will cancel each other out, which is kind of nice to know. So now I can just sort of make those go away. And tangent is sine over cosine. Now, don't forget your variables here. Even though I'm not really saying them out loud, don't forget your variables because it's important to have those as part of the expression here. And then you have 1 over the sine for the cosecant. So now we're back to converting everything to sines and cosines. And the sines cancel out. And you've got 1 over cosine of x, which is the same thing as saying secant of x. And there's the simplification of that one. Okay? Alright, moving on here, you can multiply these trig expressions as well. So, for example, let me get a little bit more room here on the first one. In example 4, we could have tangent of x cosecant of x when I distribute this tangent through to each term. And then I can go ahead and simplify this and see what comes of it. So tangent is sine over cosine, and cosecant is 1 over sine of x. And I'm not going to just mess with this one yet because I have a feeling I can probably get something to condense down. I'm always worried about condensing down with addition and subtraction because all of those reciprocal identities don't work too well when it comes to addition and subtraction. They're more for like multiply and divide. So the signs cancel, and I'm left with 1 over cosine, which is really secant. So I have secant x minus tangent x. And that's about as far as I can really take that expression. I really don't want to push a common denominator there. Okay? Knowing when to stop is kind of difficult at times. All right, now this one's kind of an interesting little problem because you've got something that looks kind of familiar to something you've done before. And that would be FOIL, of course. So if I were to try to FOIL this out, I would have sine squared of x and then plus sine of x cosine of x, and then for the inners you'd have the same thing but would be a minus, and then minus cosine squared x. Alright, now you notice that these things will just drop out, and what you have left at that point is just sine squared of x minus cosine squared of x, and that's about as far as you can take that for now. There's no other simplification for that. If you think there is, we'll get to one in just a minute. Okay, so now here is another trick that we can use, and that would be factoring. And factoring is kind of a fun thing to work on. Excuse me while I get rid of some things here, okay? And if I want to factor something, it can be just as simple as pulling out a common factor with trig functions, and that common factor here would be sine of x. So that would just be sine x times the quantity sine x minus 1, and that's the factorization of that. Not too bad. Pretty easy to do. If I look at something like what's in the middle here, this is rather fascinating because it sort of looks like a quadratic expression, except the variable is a sine function and not anything else. So if you sort of think of this as x squared minus 4x minus 32, well, certainly you can factor that into x minus 8 and x plus 4. That shouldn't give you any trouble. So this other expression with the trig functions, it's going to work the same way, except you are going to use sines instead of x's as the variable. So sine x minus 8 and sine of x plus 4, and that's how that factors. So if you see this sort of quadratic structure, think about all the possible patterns that you could use to factor those that you know from doing quadratics. Okay, one more example here, and this guy looks familiar too. This is sort of like a difference of squares pattern. So I could write this as tan of x plus 3, 3 not 13. There we go. And tan of x minus 3. That would be the factoring of that, because that's just like a difference of squares pattern, similar to saying x squared minus 9 is equal to x plus 3 times x minus 3. You remember that difference of squares pattern from Algebra 1 and Algebra 2, of course. Okay, so we'll continue on the next page here. Okay, and as we continue with the Pythagorean identities here, these are things that we know we can work with pretty easily. I know we've all seen this one before, sine squared plus cosine squared is equal to 1, but you can get the other two pretty easily, and the way that you can get the other two is by dividing by either a sine squared or a cosine squared, and you divide each and every term of this original identity by either of those things. So if I divide this one by sine squared, it's just going to be 1. If I divide the cosine squared by a sine squared, it becomes cotangent squared. Now why is that? Because cotangent is cosine over sine. And then if I divide 1 by a sine, it becomes a cosecant squared. So there's your other Pythagorean identity. Now let's go back and get the other one just by dividing everything by a cosine squared. And when I do that, the first term becomes a tangent squared. Sine divided by cosine tangent, plus 1. And that's going to be equal to 1 over the cosine, which is secant squared of x. Okay, so again, you could memorize all three of these, or you could just memorize one. I recommend just the one, as you well know by now. So moving ahead and seeing how we can apply those on simplifying some of these trig expressions here. Let's see, yeah, that's all we've got is these last two. So if I try to simplify this one right here, I'm looking for things that I can recognize easily. So I noticed that I have a sine squared and a cosine squared, which simplify to 1. So I really have 1 plus cotangent squared all over cosecant squared. Alright, now if I remember my trig identities from up above here, 1 plus the cotangent squared is equal to cosecant squared. So now that I have that, I notice that 1 power of the cosecant in the numerator cancels with that cosecant down there. So now I just have 1 power of the cosecant left, and that's all I need. All the way down to that. So what looked like pretty much of a monster of a expression really got tamed in a hurry. Let's take a look at this other one here to wrap this video up. And this one, unfortunately, is a bit of a bear, because in order for this to work, you need to get a least common denominator. And the fastest way to get an LCD in situations like that is to identify that it's going to be the two denominators multiplied together. Alright, this is a useful skill to remember even in calculus, because the LCD in calculus comes up a lot more than you think. So if I want to make the LCD be 1 minus sine x times the cosine, then This particular piece of the rational expression is just missing a cosine. Okay, no big deal. I'll just go ahead and see what I can do to add in a cosine by multiplying top and bottom by a cosine. Seems legit, right? So by cosine x all over cosine x. So I'm going to get cosine squared of x over that LCD. And then let's put a minus sign there and switch over back to blue for a minute. I'll keep red. If I want to make this part right here have the LCD, then I need to put in a factor of 1 minus sine x top and bottom. So that's going to make it look like sine x times 1 minus sine x all over that LCD of cosine x times 1 minus sine x. Okay, so now that these two things have that same denominator, now I can go ahead and combine them. So I'm going to get, let's see, cosine squared of x minus sine x times 1 minus sine x. And this is going to be all over that LCD. And you're probably wondering, why am I not distributing that cosine in the LCD? Well, I want to see if anything drops out here when it's all said and done. I just want to take my time on this one and see if anything develops to where I can cancel something out of the denominator. And those of you who are already seeing it, you can probably look ahead and say, oh yeah, I can see this coming. So let's take a look and see what happens here when I go ahead and distribute this sign in the numerator. So when I do that, I'm going to have cosine squared x minus sine x and then when I distribute that there, that's going to be plus sine squared x. And that's going to be all over this LCD. Okay, so quickly, we now see that you've got a cosine and a sine put together, and those two are going to add up to 1. So you get 1 minus sine x over cosine x times a quantity of 1 minus sine x. And then all of a sudden you say, oh, well, that's good news because the 1 minus sine x's will cancel, and at the end I'm left with 1 over a cosine of x, also known as a secant of x. So that is what those look like when we're all said and done. So there you go, folks. Head for your practice problems and give those a try, and come back and watch this if you need to.